This slidecast will cover backtracking. Backtracking is an approach to implementing a systematic trial and error search for a solution. And our example will be finding a path through a maze. So if you're attempting to walk through a maze, you'll probably walk down a path as far as you can go. And eventually you'll reach your destination and exit the maze, or you won't be able to go any further. And if you can't go any further, you will need to consider alternative paths. You'll need to backtrack until you reach a fork and follow a branch you did not travel, hoping to reach your destination. So backtracking is a systematic, non-repetitive approach to trying alternate paths and eliminating them if they don't work. So you can think about this. We're getting close to Halloween, and this would be like the strategy you might use if you find yourself in a corn maze and you're trying to find your way out. You could systematically keep track and make sure you don't just go in circles and try dead ends that you've previously encountered. Now, if you never try the same path more than once, you'll eventually find a solution if one exists. Problems that are solved by backtracking can be described as a set of choices made by a function. Recursion allows you to implement backtracking in a relatively straightforward manner. Each activation frame is used to remember the choice that was made at that particular decision point. A program that plays chess may involve some kind of a backtracking algorithm. So our problem is to use backtracking to find and display the path through a maze. And from each point in the maze, you can move to the next cell in a horizontal or vertical direction if the cell is not blocked. Our maze will consist of a grid of cells. The starting point is at the top left corner, so at grid location 0, 0. The exit point is at the bottom right corner, so at our grid sub-row size -1 and column size -1. And all cells on the path will be the background color. Barriers will be abnormal color, and the cells that we have visited will be temporary color. And if we find a path, all cells on the path will be set to the path color. Here's an example of a maze where the white cells are the background color and the blue cells are abnormal, they're barriers. So we'll enter the maze in this upper left-hand corner. That's at location 0, 0. And our goal is to reach our destination here at the lower right of the maze. And here in part B, we show the maze with a candidate path from the source to the destination. Here's a recursive algorithm to find maze path. And we have XY is going to be a location in the maze. And if the current cell is outside the maze, if X and Y, then we return false, we're out of bounds. If the current cell is a barrier or it's already been visited, then we return false. So we're off the path, or we're considering a cycle. Now, if the current cell is the maze exit, then we recolor it to the path color and return true. So we've successfully completed the maze at that point. Otherwise, we want to try to find a path from the current path to the exit. So we mark the current cell as on the path by recoloring it to the path color. So that's, at the moment, that's just sort of a guess, or we'll assume that the current cell is on the path. And then for every neighbor cell of the current cell, and our neighbors are defined as being those that are directly horizontal or vertical to the current cell. We don't consider the diagonal a diagonal cell to be a neighbor. And if a path exists from the neighbor to the maze exit, then we return true. Now, if no neighbor of the current cell is on the path, then we recolor the current cell to the temporary color visited, and we return false. Now, there is no attempt to find the shortest path through the maze. We'll just show the first path that we find. Now let's look at an implementation. This is going to be a main function where we'll have an array of colors defined and the size of the array, our main search function will go here. And here we'll have a wrapper function. So find maze path takes a two-dimensional array that will be our maze of a certain size. And that's a function that we can give to people who want to use our recursive algorithm. And this wrapper function will turn around and call find maze path, and it will start searching at 0, 0, which is the starting point. Now find maze path. The precondition is that possible path cells are in background color and barriers are abnormal. And the postcondition is that if a path is found, then all cells on it are set to the path color. And all cells that were visited but are not on the path are in the temporary color. And R and C point to a single element in our maze. And if a path through this grid is found, we return true, otherwise false. So we have a Boolean result. And here's the logic of sort of all the pseudocode we've talked about earlier. If the index R and C are outside the cell boundaries, we return false. If the color is not equal to background, that means it's either abnormal, a barrier, or it's already been part of a path, we'll return false. If R and C point to the lower left hand or the lower right hand corner of the maze, then we've succeeded. We found our destination. We set that element to be on the path and return true. Otherwise, we make our recursive case where we assume R and C is on the path, and then we call find maze path for the 4 nearest neighbors. This is the neighbors above and below and to the left and right. Okay, no diagonals. And if we find a maze path from any of those neighbors to the end, then we know we have found a path. If we don't find a path from any of those 4 nearest neighbors, then we set the current grid to be temporary, meaning it is a dead end. We won't consider it again, and we return false. Now, the effect of marking a cell as visited. Would the program still work if instead of recoloring a dead end to a temporary color, we recolored it to the background? The answer is yes. It would not affect the ability of the algorithm to find a path. It would affect the efficiency. After backtracking, the function could try to place on the path a cell that had been found to be a dead end, and the cell would be classified once again as a dead end. So marking it as a dead end the first time prevents this from happening. So it helps us later on to not sort of reconsider and sort of repeat work that we've already done earlier. Now, to demonstrate the efficiency of this approach, the author tested the program on a maze with 4 rows and 6 columns that had a single barrier cell at the maze exit. Okay, so here we'll consider all possible paths, but since the barrier's at the exit, we're never going to find a solution. And when they recolored each dead-end cell in the temporary color, it took 93 recursive calls to determine that a path didn't exist. But when they recolored each tested cell to the background color, so that we didn't detect early that this had previously been a dead end, then we took 177,313 recursive calls to determine that a path didn't exist. So it significantly increased the cost. Here's a program for testing where we can define a two-dimensional grid and give some background colors and some barriers. And then we can call the wrapper function to find a maze, basically to output the path in this grid. And you should consider a variety of test cases, such as mazes that can and can't be solved, mazes with no barriers, mazes with a single barrier cell at the exit point. And that brings us to the end of this slidecast.